Okay, section 4.2, the addition and multiplication rule. And we'll do a little bit with redundancy at the end, which actually uses the complement of a probability. Okay, if you watched the last video where I did rolling two dice, we did a little bit of the addition rule. So or goes with addition. When we get to doing probability of and with compound events, then we're going to do the multiplication rule. And each of these has a couple of criteria that we need to watch for or be aware of. Okay, so we're talking about combining two or more simple events, A and B. So we talk about the probability of A and how it relates then to probability of B. Now, we're going to have to watch out for this both occur at some point. So yeah, this is the notation, probability of A or B. And the thing in black here I'm going to underline, because we have to look out for if we're counting stuff twice. Here we go. I can do some examples now. So this is the stuff counted twice here. We have to subtract that out. So I'm going to do a deck of cards. This is why cards are so nice, because we can easily do probability with them. And I'm going to do draw one card. So you know there's 52 cards in a deck. And I'm going to do what's the probability of me drawing a 9 or 10. Well, it's the probability of the 9 plus the probability of the 10. And then I subtract out if they both can happen, but we don't worry about this because a 9 and a 10 don't overlap. They can't be the same. So in this case, this is 4 out of 52 plus 4 out of 52 is 8 out of 52. I don't worry too much about you reducing right now, because this shows me your thinking and I can see your work. So this shows your thinking. Now, this disjoint or mutually exclusive. I'll go back to what I did with my deck of cards. Over here, I have the 9s. I have 4 9s. So this is kind of the set of 9s. I have 4 of them in here. I have the set of 10s over here. I have 4 of them. There is no overlap. They're disjoint, mutually exclusive. They can't occur at the same time. So in this case, then P, A, or B is simply probability of A plus probability of B. There's no overlap. We don't have to worry about that. Now, if they're not disjoint, which I suppose I better do up here now. Okay, let's look at things that are not disjoint. So not mutually exclusive. That would be something like this. Suppose these are the kings, set of kings. These are the red cards. Well, I know there's overlap because there's some kings that are red. There's 2 red kings in here. And there's 2 more kings out here, the black ones. There's 26 total red cards. So there's 24 red cards out here. So if I want the probability now of king or red, I do the probability of the kings plus probability of the red. But now I subtract out the probability of king and red. Erase this a bit. So what I'm getting here is probability of king I'll do it in a sentence here, plus red, plus probability of king and red, plus. I know I got to subtract that out. I was thinking about what I was doing. Probability of king, 4 out of 52. Probability of red, 26 out of 52. Now, show me your thinking by demonstrating that I have to subtract out the 2 red kings because they were counted twice. So it's 28 out of 52. That's how we handle problems that are not mutually exclusive, where there's overlap. If we were doing set theory, we would talk about intersection. This is the intersection of these 2 sets. So when I'm subtracting P, king, and red, that's subtracting the probability of the king intersect the red, where they overlap. So that's what we have to worry about with an OR. Is there intersection or overlap that we're going to have to subtract out? There you go. That's the intersection. We have to subtract it out or ignore it. Or just count it once. Can't ignore it, my bad. Complementary, I've introduced this before, where also in set theory, that's the complement of A by putting the bar over the top of it. So a probability adding its complement add up to be 1. So we can use these to find one if we know the other. Simple algebra. So here's a quick one. If I know the probability of someone who's sleepwalk, so if we say probability of sleepwalk is 0.292, then the probability of people who don't sleepwalk is 1. Subtract that. So we'll do this a lot in this class, is find complements of events, or complements of probabilities, I should say, to be much more accurate. Okay, the next rule, multiplication rule. And. Now, we're going to multiply when we see and, but we do have to assume right here that the first event has already occurred. And I'll do a couple of examples that demonstrate that. So I'll do it right here. Let's think of a deck of cards again. I'm going to do two examples. I'm going to do one with replacement, meaning I put a card back in the deck. So I'll do that first. I want to find the probability of drawing two aces. So the probability of the first ace, which I will put here, and then the probability of the second ace, I will put here. And I'm going to multiply those. So the first one, well, that's 4 out of 52. And now here's where the with replacement comes back. I put them back in the deck. So there's still 4 aces and there's still 52 cards to draw from. I multiply those, I get 16 over, I believe it's 2704. Better check. Yes. Now, what if I do this without replacement? And here's where the black writing comes in, the bolded writing, assuming that A has already occurred. So this is without replacement, which is that as an abbreviation. So what's the probability? I draw 2 aces. Okay, again, it's the probability of the first times the probability of the second. Probability of the first ace is 4 out of 52. Now what changes? We assume that we got an ace. That's this. Well, I'm not putting the card back, so there's only 51 left to draw from. And there's only 3 aces left because I have one in my hand. That's where the assume that event A has already occurred. So this is 12 divided by 2652. Again, this shows me your thinking. This should be a multiplication. I don't know what happened to that slide. So when we're doing multiplication, we think of independent and dependent. Well, if you think back to the example I did with the cards, with replacement, they were independent. It's up here. Remember, I put the ace back. So when I went to draw again, the fact that I had an ace did not affect the probability of me drawing an ace again. Without replacement, suddenly they're dependent. Because I had the first ace in my hand, I did not put it back. Therefore, that affected the probability of the second because there weren't as many cards in the deck. There's only 51, and there's only 3 aces left because I already had one. So when we're dealing with cards, if I say, what's the probability of dealing you 2 cards? So now I'm dealing 2 cards. Okay, that's without replacement because you're holding one. Heck with 2, let's do 3. What's the probability of getting 2 aces and a king? That's my symbol for and. Maybe I should write it in there because it almost looked like an addition, and that's my bad. Okay. Now, we have 3 cards. We're being dealt 3. First, second, third. Okay, the probability of getting an ace is 4 out of 52. Now, I'm not putting them back, so there's only 51 cards left in the deck. There's 3 aces left. Now I have 2 cards in my hand, so there's only 50 left, but there are 4 kings out there. You multiply that together, you get 48 over 1,326,100. So notice what's happening with these numbers. These are staying small, but these are getting really big really fast. So that's a pretty small probability that you would get 2 aces and a king when you're dealt 3 cards. So test results from subjects who use drugs. So we get positive test result. That's good. Negative test result. This is a false negative because we know they use drugs. They should all get a positive, but sometimes you get a false negative. Other cases, a false positive. Okay. If 2 are randomly selected with replacement, we're putting them back, so they're independent. Positive, and the second one had a negative. So part A, I'm drawing 2. I always do this when I'm multiplying. It's like the counting rule that I introduced before. Well, let's see, probability, the first one is positive. That's 45 out of 50. Then I multiply by the probability second person had a negative. That's 5 out of 50 because it's with replacement. I put the other one back in. Now what's different in part B? This is 45 out of 50. Now there's still 5 in there that are negative, but I'm holding this one, not putting it back, and it changes it to 5 out of 49. These were dependent because when I did the first one, that affected the outcome of the second one. I just did all this. Sometimes we make samples from large populations, and even though they're actually dependent, like if I was to select 2 students from the population at BC and surveyed them, I'm not putting them back in, so they are actually dependent, but because they're so small, they represent so few of the total population, I can treat them as independent. So here, there's our adults in the United States. If I select 3, that's such a small percentage of the total number of adults. I'm just going to treat them as if they were with replacement. That's all that's saying. Okay, last topic in this section is redundancy. And I'm actually going to use the complement to do this problem. Yeah, we have 2 of a lot of stuff, and 2 eyes, 2 kidneys, things like that. So that's redundancy. So here's a plane. Hydraulic systems, they have 3. So if anyone fails, they still have 2 other ones to fall back on. The hydraulics run the wings and the landing gear, pretty much everything on the plane. So let's see. If we had one hydraulic system, what's the probability that the aircraft's flight control would work for a flight? Well, the probability that one would fail is this. So the probability that they work is 1 subtract the probability of the complement, which is fail. That's 1 subtract 0.002. That's 0.998. I don't know. It's large, but it's not 1. So maybe I don't want to be on that plane. Because the thing about probability is stuff can happen, even if it's low probability. Now let's do it with 3. So now it's the probability of work, all of them work. Well, the complement of that is 1 subtract the probability that they all fail. So this is 1 subtract the first one fails, and the second, and the third. That's the 0.002 multiplied by itself 3 times is 1 subtract 0.002 to the 3rd power. And now I'm at 0.9999992. I feel much safer about getting on that plane. So this is the problem where we actually use the complement here to make it easier to do. The next section will actually do that for a lot more problems. And I just did that. There's my white space to do it in, but I'm already done. See you next time. Let's see, I'm trying to do something. Oh, stop recording.